Welcome back. This is 6.2.3. We'll introduce a tables of pairs of Fourier transform. We'll go through some examples and discuss the properties. Let's look at the common DTFS and DTFT pairs. Typically, a table will be given such. A table will look like this. On the left, you have xn. So here will be the time sequence. In the middle here, x omega shows you the DTFT of this time sequence, and once in a while you have a condition. When this condition is true, then the DTFT exists. Let's examine the first one. In this particular example, we have a value that is going to be increasing with respect to n. So alpha can be some value to the power of n. So, and it only happens on the causal part, n equals to 0 to infinity. Now, if a is greater than 1, so for example 2 to the power 1 is 2, to the power 2 is 4, so it keeps on increasing. If it keeps on increasing, then you'll realize that DTFT do not exist because the whole sum does not converge. So here it says that only for condition a is less than 1, the absolute value of a is less than 1, thus x omega looks like this. In fact, this looks very similar to the Z transform or the Laplace transform of the exponential signal. And you have more of these examples here, and typically in this course you can just use some of this lookup table unless the question explicitly asks you to derive from a given xn to x omega. Now, how do I know that these are aperiodic signal? Well, of course you can plot xn and then see that they are aperiodic, and therefore we are getting the x omega for an aperiodic sequence. But how do we quickly also realize that these are aperiodic sequence? Oh, you know cosine and sine and ej omega not n these are actually periodic signal. Now, if you look at the DTFT, the most telltale sign that these are periodic signals is that in the DTFT of periodic signal, then you will see the deltas coming out. The deltas representing that only certain frequencies are occurring. And when only certain frequencies are occurring and no other frequencies are occurring, then it basically shows you that even though x of omega is continuous, only some frequencies are happening, and only this particular frequency is happening because this particular frequency is periodic. Okay, so that's how we see this table of x omega. Now we further continue with more signals of interest. So this is of course the function, the most famous one of them all, where you have a function that is, what do you call that, non-zero at a certain value. So this is minus n and this is n, and then this is non-zeros over here, and then you have a sinc function. You also have a comb where this is simply this function over here. The comb and the Fourier transform, the DTFT of a comb is also another comb. And then you have the sinc function here. Notice that this is a sinc function, and then when you have a sinc function in the time, you also have a sinc function in the frequency. Sorry, you will have the rectangular function in the frequency. So in fact, these three functions are very, very important, and I have also computed them by hand for you. So go to chapter 6.2 handout 1. You'll see that I have derived the DTFT of these 7 functions for you, and please go ahead and take a look at how I derive them. I will not go through this in great details in the recordings. Instead, I provided you with a detailed handout as well as a list of videos that you can see to derive this by other lecturers online. With that, I've completed the DTFS and DTFT transform pair along with this handout. Thank you.